Today we will discuss one of the most common forces you will come across while solving problems in statics, that is gravity. We have already used gravity in the previous few videos, so by now it should be intuitive how this works. However, gravity while dealing with particles and while dealing with bodies behaves slightly differently, so we'll be going into those aspects today. So first, let's start with the simpler of the two, that is the particle. I have represented a particle over here by this box. The particle has a mass m and there's a downward acceleration due to gravity vector g. So this is quite simple. The force on the particle because of gravity will be a downward force, basically a force in the direction of the acceleration due to gravity, and the magnitude of the force will be the magnitude of the mass into the magnitude of the acceleration due to gravity, which in our case is mg. So the higher the value of g or the higher the value of m, the higher the value of the force. And this force is called the weight. M is the mass, mg is the weight. So this is basically gravity as far as the particle is concerned. Now let's move to the body. This body I have depicted in a general shape over here. Now the way we can deal with this body is we can imagine the body to be made up of many small particles. Each particle is infinitely small and hence has very little mass in it. So let's take one such particle and expand it. So this particle, not unlike this particle, has some mass, but in this case the mass is not m but dm, where dm represents a very small portion of m, and again there's the acceleration due to gravity vector. So we can treat this like any particle and we say that it is experiencing a downward force of dmg. So this is the force experienced by this particle. Similarly, this particle, this particle, this particle, all particles in this body are experiencing this force. This force is divided all over the body. Now what we can immediately see is this system as is difficult to understand and is difficult to use. But what we have studied previously is equivalent systems of forces and moments. That is, we can take an identical body. So I'll try my best to make a body which looks identical. And we can, at any one point, any arbitrary point, we can replace this entire system by one force and one moment. So we know that the value of this force is sigma fi, but in this case we have an infinite number of very small forces, so this becomes an integration of all the individual forces over the volume. So this circle represents volume of g into dm, and doing this integration we can see that this becomes mg. So the value of this force, and since g is in the downward direction, this will actually be mg. So the value of this force is equal to minus mg, and this is independent of the position of this point. And similarly we can calculate the value of m. M is also such an integral. Over here it has to take into account the different position vectors, basically the position of this point. Now what's important is that we can actually move around this point, and for those of you who've gone through the lecture on equivalent systems of forces carefully would know that as we move around this point at different points in the body, the value of this force remains constant, but the value of this moment changes as we move around. So let's do one thing. Let us plot all those points on which the value of this moment is equal to 0. So what you will notice is that we'll get a straight line somewhere placed on which if we take any point and get the equivalent system of these forces, the value of m will be 0. Now this line will also be parallel to this vector. Now suppose we change the direction of this vector. Instead of gravity acting in this direction, we have a different direction of gravity called g dash, and we carry out this exercise again. We mark all the points on this body on which if we take the equivalent system of forces from this system of forces over here. So in this case, the equivalent system of forces will change. We'll have forces in this direction, and we make an equivalent system of forces over here, and we take all the points on which the equivalent system of forces gives no moment. Then we'll get another line. This time the line is parallel to this, and similarly we can take a lot of different directions and we'll get a lot of different lines. And the intersection point of these lines is called your center of gravity, which I will represent by COG. Basically, irrespective of the direction of your gravity vector, if you take the equivalent system of forces over here, there will be no moment and the force will simply be represented by minus mg. So in short, what we do is we calculate the position of the center of gravity, which is a concept which is slightly involved, so we will not cover this, but let's just assume that you know where the center of gravity is. We can replace all of these forces by one single large force of magnitude mg. So in one of the initial videos on the differences between a particle and a body, what I had mentioned was that in a particle, the exact location of the force is not important since a particle is infinitesimally small. But in a body, the exact location of the application of force is important. So we can see this as a manifestation of that in the particle I just drew a force mg, and it doesn't matter where it's acting on the particle because the particle is really small. But over here, I drew a force mg, and I had to be careful that I ensured that it passed through this very special point called the center of gravity. So that is all as far as gravity is concerned.